In our study of circuits, we looked at RC circuits, then RL circuits, and then most recently, in the last few videos, we looked at LC circuits. And so now, it shouldn't come as a surprise that we're now going to look at a circuit with an R and an L and a C. And one way of saying why it's important to do this is the following. I hate to break it to you, but there is no such thing in nature as a pure LC circuit. There's no such thing in human-made technology of a pure LC circuit, because in any circuit with an L and a C with current flowing, the current has to flow through real wires, and those wires have resistance. So we're now going to add a resistor in the circuit, and you can, if you wish, think of this resistance R as representing the resistance of the wire in this inductor, the wire in the circuit, or you can think of it as representing an extra resistor that you added to the circuit to make an RLC. It doesn't matter. The physics will be the same. But any real circuit with an L and a C in it also has some R, and now we better put that R in. So, well, let's use the tools that we've developed over the last few videos. Let's analyze this circuit. Let's turn it into a differential equation. Let's see what we get. I'm going to choose the current to flow this way this time. The reason I'm going to choose the current to flow this way is that I will then have that I is plus dq by dt. Because by Q, I've decided by Q, my convention is going to be that Q is the charge on this top plate. And if the current is positive in this direction, that means the Q on the top plate is increasing. So I've chosen signs such that I is plus dq by dt. And now let's analyze this circuit. And I'm going to analyze it the way we've learned how to do. I'm going to imagine I close the switch, and I've stuffed this capacitor with a charge Q naught. We learned how to do that several videos ago. And so I've got this capacitor. It's stuffed with charge Q naught. Then I close the switch. Now what happens? Current is going to start flowing this way, and then there's going to be an oscillation, but we have to see what the resistance will do. But if the resistor wasn't there, we know what happens. You get an oscillator with a current going back and forth, back and forth, back and forth, as we've discussed. But now let's analyze this circuit with the R in it. So I'll start here. I'll walk my way around. When I cross the capacitor, what I get in my differential equation is Q over C crossing the capacitor. Then I cross the resistor. And because the current is going this way and I'm crossing the resistor this way, I get a plus IR. And then I go through the inductor, and because the current is going this way and I'm going against the current, I get a plus L di by dt. And then I come back through the switch, which is now closed. I get back to where I started, and that gives me a 0. So this is my differential equation. And you notice that when we had just a C and an R, we had a term with a Q and a dq dt. When we had just an R and an L, we had a term with an I and a di dt. When we had just an L and a C, we had a term with a Q and a di dt. And di dt was d squared Q by dt squared, and that gave us the oscillator. Now we have all three terms. We have a Q, we have a dq dt, and a d squared Q by dt squared, all in the same equation. This makes this a harder differential equation to solve. And in 802, we're not actually going to assume that you have the math background to solve this differential equation, but we'll nevertheless be able to analyze it and understand what happens. OK, so the way I'm going to analyze this, the first thing I'm going to do to simplify this, you'll see how this simplifies this as we go along, is I'm going to multiply every term by I. So if I multiply every term by I, what do I get? Rewrite the equation. So Q over C times I, and I is dq dt, plus multiplying by I get I squared R, plus multiplying by I get Li di by dt, and this is equal to 0. I've just rewritten the equation after multiplying every term by I. OK, now I look at this and I notice that here I have a Q dq dt. That's the derivative of Q squared, divided by 2. Here I have an I di dt. That's the derivative of I squared, divided by 2. So I'm going to collect those terms the first term and the third term, and write them as the derivative of something. So it's d by dt of something. And then that will be, I'm leaving out the I squared r term on the left, so that has to move over to the right. So that's going to be, whatever that something is, its derivative will be minus I squared r. OK, now what's the something? The something has two terms. One term here is q squared over 2c. Because the derivative of q squared is 2q dq dt. And I divide by 2c, and I get what I had here. Similarly, for this term is d by dt of what? It's d by dt of I squared L divided by 2. Again, differentiate this with respect to time. Differentiating I squared, I get 2I times di dt, multiply by L over 2, and I have what I wanted to have. So this is the differential equation that you get from this circuit. And now we notice that we can interpret this. What this says is that d by dt of, what's q squared over 2c? Well, that is the energy of the electric field in the capacitor. What's I squared times L divided by 2? Well, that's the energy of the magnetic field in the inductor. And that is then set equal to minus I squared r. So what this circuit describes is an oscillation between the L and the C with the energy sloshing back and forth between electric and magnetic, as we've seen. But the energy in the L plus the C, this is the energy in the C, this is the energy in the L, is not conserved anymore. It's decreasing. It's decreasing with time by an amount I squared r. Why is it decreasing with time? Well, it's because as the current is going back and forth, back and forth, back and forth, it's always going through this resistor. So there's a current going back and forth, back and forth, back and forth through the resistor. And when a current flows through a resistor, it generates heat. It dissipates energy. And that is the loss in the energy stored in the capacitor plus the inductor. So previously, when we had no resistance, this quantity was conserved. D by dt of this was 0. Adding the resistance in the circuit means that the energy stored in the capacitor plus the inductor together is no longer conserved. So as the energy sloshes back and forth, with each slosh back and forth, some of the energy is dissipated into heat as the current flows through the resistor. And this is the picture of what happens in an RLC circuit that you should take away from this differential equation. You are not responsible in 802 for knowing how to solve this differential equation, but I will tell you the solution. And then you can just use straightforward differentiation to check that the solution that I'm about to give you is indeed a solution to this equation. Well, it's a solution to this equation as long as, so remember that the angular frequency of the LC oscillator was omega naught, which is 1 over square root of LC. And I am going to assume that this omega naught is bigger than r over 2L. And we'll see why I had to make this assumption in a minute. But I'm going to assume this. And if I assume that, in other words, I assume that r is not too big. This is a statement that r is not too big. If r is small enough, this is going to be satisfied. And I claim that if I make this assumption, then here's my solution. I'm just going to write it out for you. My solution to this differential equation, written here, or written here, or written there, is going to be q as a function of time. Remember, I here is dq dt. So you write this as a second order differential equation for q. And here's the solution. It's proportional to q naught. That's the initial charge on the capacitor, times e to the minus r over 2L times time. There's an exponential decay times a cosine. It's not cos omega naught times time. It's cos omega prime times time, where omega prime is equal to the square root of omega naught squared minus r over 2L squared. Okay, so it's a straightforward exercise in differentiating this function for you to go and check that if you differentiate this function twice and put it here, because this, remember, is d squared q by dt squared, differentiate this function once and put it there, because I is dq dt, and then check, and you will see that this function solves this differential equation as long as omega naught is bigger than r over 2L. And you can see that if omega naught were smaller than r over 2L, something bad would happen here. And in fact, what that means is that if omega naught is smaller than r over 2L, the solution to the equation takes a different form, which we will not be using here, because we're going to assume that r is small, that basically what's happening is like what we saw in the LC circuit, with the energy going back and forth, back and forth, back and forth, but losing a little bit each time. Losing a little bit each time, that means r is small. And the smallness of r quantitatively means that r over 2L is less than 1 over square root of LC, which then means that this omega prime is a sensible definition. Okay, there it is in math. What does this look like if I plot it? So here's my q of t. So q of t, q plotted as a function of time. It starts at q naught, and it oscillates. But as it oscillates, the amplitude of the oscillation decreases. So this function, q of t, right here, with that definition of omega prime, is what I've plotted right there. And the envelope of this oscillation, this decaying envelope, is the exponentially decaying function, e to the minus r over 2L times t. And the function itself is this envelope, this exponential decay, multiplied by a cosine, so a periodic function. And you can see that the actual function shown in that I wrote as a solid curve here is the envelope multiplied by a sinusoidal, in this case a cosine function. But when you check the math, you will discover that it's not cos of omega naught t, it's cos of omega prime t, where omega prime is a little bit less than omega naught. And this is the solution to this differential equation, which means this is the answer to the question of how the charge behaves as a function of time in this RLC circuit. But to be clear, I'm not expecting you to learn how to go from this differential equation to this solution, because I didn't teach that to you. I pulled the solution out of my hat, wrote it on the board, and you can check that I gave you the right solution, but I don't expect you to be able to go from here to the solution. That takes more math than we're assuming you have in 802. But the intuition is what's important. And the intuition you actually get at this level here. The intuition of this solution is the sinusoidal oscillation. The energy is sloshing between electric, magnetic, electric, magnetic, electric. But when we got back here, we don't have as much energy as we did when we started, because when the energy went from electric to magnetic to electric to magnetic, each of those sloshings back and forth corresponds to a current flowing through the resistor, and as the current flows through the resistor, energy is dissipated. And that means that by the time I get back to here, I'm back to the energy being all electric. There's no energy in the inductor, it's all in the capacitor. But there's less energy in the capacitor here than there was there. And then there's even less here, even less here, even less here, according to this exponentially decaying function. That intuition is what you should take away from this derivation.